This is Module 7, Section 2.7, linear inequalities, and with those inequalities we're going to look at solving, and we're going to look at graphing inequalities on a number line. In Module 6, we reviewed the four basic types of inequalities. As opposed to equations, remember equations have an equal sign. They were given in this table, and we're going to look just very briefly at them. Remember, the arrow that points to the left is the symbol for less than. Reading left to right, A is less than B would be an example. Given numbers, a true statement might be 3 is less than 5. The arrow with the equals portion shown next, pointing to the left, is less than or equal to. Again, example might be 3 is less than or equal to 5, or even 5 is less than or equal to 5. Remember that the two only have to be one or the other. They don't have to be both. The arrow pointing to the right is greater than. A is greater than B. And greater than or equal to has the equals portion. A is greater than or equal to B, or A is greater than or equal to B in words. Just as with equations, if a value gives a true statement in any inequality, then it is considered a solution to that inequality. With most inequalities, there are an infinite number of values that will make an inequality true, unlike just maybe one or two solutions with equations. Therefore, we are interested in finding a way to represent the set of all possible solutions, which is the same or equal to our solution set. For example, reading left to right, x is less than 5 means that all numbers less than 5 are solutions. Therefore, 4 is a solution because 4 is less than 5. That's true. 0 is a solution because 0 is less than 5. Also true. 4.9 repeating is a solution because 4.9 repeating is less than 5 as well. That's true. And you would agree with me, if you think about that, there are an infinite number of solutions that you could come up with that would work. So simply listing out the solutions will no longer work as it did for equations. We need a better way to represent the infinite solution set, or the infinite amount of numbers that make an inequality true. Number lines are a great visual way to represent solution sets for inequalities. There are two number line graphing symbols traditionally used for graphing inequalities on a number line. And they are the closed dot symbol, which is represented by a point that is included, and you use a closed dot for inequalities that are less than or equal to or greater than or equal to. And then there's an open dot representation where the point where the open dot is located is not included, but is rather a starting point. And open dots are used for less than or greater than inequalities. So let's look at an example. I want you to graph the solution set for a number line, on a number line for the inequality x is less than 5. So to do that, of course, you'd first have to draw a number line and put as many or as few labeled ticks on there as you want. I'm going to go ahead and just label several ticks for this first example. Now, you would agree with me that in terms of values that would make that inequality true, we said that 4 would work, 3 would work, 2 would work, 1 would work, 4.9 repeating would work. Okay? Now, could you then put in a whole bunch of dots to represent those solutions? And this is a common mistake. This is not correct. A lot of times students will say, well, everything less than 5 will work, so I'll just put a dot on every one of those integer numbers and that's my solution set. The reason that's not correct is because you're missing all of the numbers that are in between all those dots. For example, you would agree with me that if I picked halfway between 3 and 4, 3.5 is less than 5, so that's also a solution. So would 4.9, we already talked about that. 4.9 is less than 5. So then another mistake that students make is they say, well, then I'll just put an infinite number of dots along that number line. The problem with that is anytime you're making finite dots, there's always room between those dots where a number would occur that's not included. Or another way to think about that is if you put dots one right after another, right next to one another, what that ends up looking like is a line. And so, to graph an inequality on a number line, we're not going to put a series of dots. We're instead going to draw a line to represent all of the numbers that are included, because there's an infinite number. The question then becomes, though, well, what about 5 itself? Okay? Could x be equal to 5 be a solution to that inequality? And the answer is no, because if you put 5 in for x, you get this expression. 5 is less than 5, and that's false. 5 is not less than 5. So what that means is, although we have a line that extends to the left from 5, 5 itself is not included. And so to indicate that 5 is your starting point, because anything just slightly less than 5 does work, we're going to put an open dot on 5. And again, if you look at the definition above, an open dot on a number line means that that point itself is not included. 5 itself does not work, but everything to the left or less than that does work, as indicated by the arrow. So the correct way to represent that is an open dot at 5 with an arrow extending to the left. All numbers less than 5, not including 5, do work. Now, the next question I often get from students is, well, Lisa, why didn't you go ahead and put that open dot on the number line and then extend the line actually on top of the line? And my answer to that is that's fine, but the problem with putting it on the line is if I'm drawing this, let's say, in pencil and I don't have multicolors, it's really hard to see where that line is extending if it's right on top of the number line that you drew. So I choose to write it just slightly above the line so that I can easily see that line. All right, so let's just do some other examples. Let's graph x is less than or equal to 5 on a number line. Now, that's very similar to the problem we just did, except that now, instead of just less than, it's less than or equal to. So again, draw your number line. At a minimum, you have to have your reference or your starting point on that line. So you have to have a 5 on your number line. If you want to put other ticks and label them, you certainly can. It's not necessary. Remember that with number lines, lower numbers are always to the left, higher numbers are always to the right. All right, so here, x is less than or equal to 5. You would agree with me that 4, again, would work. 3 would work. 0 would work. 4.9999 would work. And so just like before, we want to extend our arrow to the left. Anything less than 5 works. But unlike the previous example, we also could let x be 5 itself. Okay, the question is, could x be equal to 5 and still make the above true? If you plug that in there, you get the inequality 5 is less than or equal to 5. Is that true? Well, yes, that is true, because 5 is equal to 5, and it has to be one or the other. It could be less than, which it isn't, or it has to be equal to, which it is. So because 5 itself works, as well as everything less than 5, we're now going to use the closed dot symbol as opposed to the open dot symbol. Closed dot means that the value that the closed dot is actually on is also included. Graph x is greater than 5. Okay, draw your number line. At a minimum, you need to have that 5 labeled on your number line. Now, x is greater than 5. We're interested in values of x that make that true. you would agree with me that 6 would work. 6 is greater than 5. 7 would work. 7 is greater than 5. 5.1 would work. 5.1 is greater than 5. Visually on our number line, that would be all numbers to the right because larger numbers are to the right. So now the only question is, would 5 itself work? If you let x be 5, do you get a true statement? Is 5 greater than 5? The answer is no. That's false. Therefore, instead of using the closed dot symbol, we need to use the open dot symbol at 5, meaning 5 itself is not included, but everything larger than 5 does work. X is greater than or equal to 5, exactly the same as the problem above it. Everything to the right or larger than 5 will work. The difference, though, is now 5 itself will work because 5, although it's not greater than 5, it is equal to 5. So 5 is equal to 5 falls in this category. We now need a closed dot as opposed to an open dot. However, what do you do with a problem that does not have the variable isolated, like this example? 2x plus 6 is greater than 5x minus 7. At this point, you couldn't just draw a number line and represent all the x's that make that true because you haven't solved for x. You don't know what number x is referred to. So what we're going to have to do for this problem is this. You can solve for your variable just the same as if that was an equality, just the same as if that was an equal sign, except the one thing you have to remember is if you multiply or divide by a negative number, you reverse or flip the inequality sign. And what I mean by that is this. If your original problem is less than, and you multiply or divide by a negative number and have to flip the sign, when you flip a less than sign, it becomes greater than. So you flip it left to right. Less than or equal to flips over to give you greater than or equal to. Greater than flips or reverses left to right to become less than. And greater than or equal to reverses or flips to become less than or equal to. All right, so let's summarize how to solve inequalities, and then we'll do some examples. We said that you're going to solve inequalities exactly the same as equalities, except for that one exception that we just talked about. So your first step for any inequality is remove any parentheses using distributive property, etc. You want to get rid of the groups so you can move stuff around. Your second step is going to be to clear fractions, just like with equalities, by multiplying each term by the least common multiple. Third step, clear decimals by multiplying each term by the appropriate multiple of 10. Fourth step, combine any like terms on the same side of the equality sign. Remember, you can't combine like terms across an equal sign. You can't combine like terms across an inequality sign either. Step 5, get your variable terms on one side, all your constants on the other side. And to do that, just like with the equalities, you're going to use the addition or subtraction property of inequality. Move stuff around using addition or subtraction. And then isolate your variable or solve for the variable by using the multiplication or division property of inequality. If multiplying or dividing by a negative number, remember to reverse or flip the sign. Only multiplying or dividing by a negative number. And then, as always, you want to take your answer, check it in the original problem to make sure that it works. So let's do some examples. This is the previous inequality that we introduced this section with. So we want to solve this inequality and graph the solution set on a number line. So we want to isolate x, just as if that was an equal sign. So I'm going to choose to get my x's on the left-hand side and my constants on the right. So I'm going to start with that 5x. That's a positive 5x, so I want to subtract 5x from both sides of my inequality. Because I subtracted, the sign will remain the same. Signs never flip with addition or subtraction. So do the math. 5x minus 5x is 0, so it's gone. The sign remains the same. Okay, if the 5x and minus 5x gives us 0, that leaves us, of course, with 0 minus 7, or just negative 7 on the right-hand side. Left-hand side, 2x minus 5x is negative 3x, and I still have that plus 6. Notice the sign remains the same because all I did was subtract. Okay, next step, I want to get my constants on the right-hand side. So I'm going to subtract 6 from both sides. That'll cancel it out on my left-hand side, or leave me with a 0. So I've got negative 3x. Now I subtracted, but addition and subtraction never changes the sign, so the sign remains the same. Over on my left-hand side, negative 7 and negative 6 is negative 13. You have to isolate your x. So my next step is to divide both sides by negative 3. And when you divide by a negative number, the rule is you must reverse or flip the sign over. So the greater than symbol becomes a less than symbol. Nothing else flips. The numbers stay where they were originally. Just do the math. Negative 3 divided by negative 3 is 1. 1 times x is x. Right-hand side, negative divided by negative is a positive 13/3. Reduce that fraction if possible. In this case, it's not. You could write it as a mixed number if you wanted to. That's up to you, depending on how comfortable you are graphing on a number line. If you wanted to convert that to a mixed number, 3 goes into 13 4 times with 1 left over. All right, so that's your solution. You've got your x isolated. Now we're asked to graph that solution set on a number line. So as before, draw your number line. At a minimum, you have to have that starting point, 13/3 or 4 1/3. The problem is x is less than that, so that means all values to the left are solutions. But since it's less than and not less than or equal to, you're going to put an open dot actually on 13/3. And that's your solution. Let's do another one. Negative 8 plus y is greater than or equal to 1. We want to isolate our y. So here we have a negative 8. To get rid of a negative 8, we're going to add it to both sides. That'll cancel it out on your left-hand side. Addition does not change the sign, so the sign stays the same. Now we're left with y is greater than or equal to 1 plus 8 is 9. Our y is isolated. Our solution set is listed. We want to graph that, so draw your number line. At a minimum, you have to have a 9 on there. We're interested in y values greater than or equal to, so that means that the line is going to extend to the right. And 9 itself also works, so it would be a closed dot on the value 9. Y is greater than or equal to 9. Next example, 3 minus 7x is less than 10 minus 8x. Again, we want to isolate our x, so I'm going to choose to, again, put my x's on the left-hand side. It doesn't matter what side you isolate your x on. I'm going to choose to move my x's to the left, though. So if I add 8x to both sides, it cancels out on my right-hand side. And on my left-hand side, of course, my 3 is still there. Negative 7 plus 8 is a positive 1, so that's plus 1x, or just plus x. I added, so my sign remains the same, is less than 10. Okay, I've chosen to get my x's on my left-hand side, so my constants are going to be on my right. I'm going to subtract 3 from both sides. Now I've got 1x, or just x, is less than, again, the sign does not change because I'm subtracting. 10 minus 3 is 7. My x is isolated, so my solution is x is less than 7. Draw my number line, make sure I have a 7 on it. I want values less than that, so the line will extend to the left. And since it's less than 7 itself doesn't work, we need an open dot symbol. All right, so let's look at this next example. We've got 7 times the quantity x plus 1 minus 6x is greater than or equal to negative 4. All right, first step, get rid of any groups. So we want to distribute our 7. That would give us 7 times x is 7x, plus 7 times 1 is positive 7, minus 6x is greater than or equal to negative 4. The sign does not change because I did not multiply or divide both sides by a negative value. Okay, sticking with my left-hand side, we've got some like terms on the same side of the inequality I can combine. So 7x minus 6x leaves us with 1x, or just x, and then I still have that plus 7 there, is greater than or equal to negative 4. Now, to isolate x, I want to subtract 7 from both sides. Subtraction never changes the sign, so the sign remains the same. I've got x on the left-hand side, and negative 4 and negative 7 is negative 11. That's my solution. I want to graph it on a number line. Draw your number line. Put negative 11 on there. X is greater than or equal to negative 11, so that line extends to the right, and we have a closed dot at negative 11 to indicate negative 11 is included in that solution set. Next problem, 1/4 times x plus 4 is less than 1/5 times the quantity 2x plus 3. Again, you want to distribute that 1/4 and that 1/5 to the group that follows it using distributive property to get rid of any groups. So I'm going to write that out longhand since we've got fractions. We've got, for our first step, 1/4 times x is 1/4 x, plus 1/4 times 4, and remember that 4 can be written as 4 over 1 to make it a fraction, is less than 1/5 times 2x, remember that 2x is in the numerator, plus 1/5 times 3, or 3 over 1. All right, let's clean that up. 1/4 times x, not much you can do with that. That's 1/4 times x. Plus, all right, notice that this is a multiplication step of fractions. We could take a common factor of 4 out. We can cross-cancel. So 4 divided by 4 is 1. Here, 4 divided by 4 is 1 as well. And notice that that term, after you cancel, gives you 1 times 1 up top and 1 times 1 in the basement, which is just 1. So we'll clean that up next step. Is less than. All right, this next multiplication step, multiply top and bottom, nothing to cross-cancel. So 1 times 2x is 2x. 5 times 1 is 5. Plus, again, for this last multiplication step, there's nothing to cross-cancel, no common factors. So 1 plus times 3 is 3, and 5 times 1 is 5. Okay, so cleaning that up once more, we've got 1/4 times x plus 1 is less than 2x over 5 plus 3 over 5. All right, next step. Just like with equations, we're going to clear fractions. So look at all of the denominators in the problem. We've got a 4 and a 5. And ask yourself, what would be the least common multiple of 4 and 5? The answer is 20. So we're going to clear fractions by multiplying each term by 20. Remember, terms are separated by addition, subtraction, equal signs, or inequalities. So we're going to multiply everything by 20. Don't forget this term that doesn't look like a fraction, but you still need to multiply it by your least common multiple. So we're going to do that up over here. We've got 20 times 1/4 x plus 20 times 1 is less than 20 times 2x over 5 plus 20 times 3/5. Okay, recognize those 20s can be written as a fraction by putting it over 1. 20 divided by 1 is still 20. And that just emphasizes that those 20s are up in the numerator. So for each of those multiplication steps, just like before, we should be able to cross-cancel out our denominators. Notice there's a common factor of 4 here. 4 divided by 4 is 1. 20 divided by 4 is 5. Okay, this next term here doesn't have any fractions in it, so I'll just skip that one. Next one on the right-hand side of the inequality, there's a common factor of 5. 5 divided by 5 is 1. 20 divided by 5 leaves us with 4. And over here on our last term, we have a common factor of 5. 5 divided by 5 is 1. 20 divided by 5 is 4. If we did that correctly, all our denominators should now just be a bunch of 1s, and we can ignore them. So just do the math up in the numerator. For our first term, we've got 5 times 1 times x. That's 5x. Plus 20 times 1 is 20, is less than 4 times 2 times x is 8x, plus 4 times 3 is 12. Now we have a problem very similar to the ones we've been doing. So I'm going to choose to get my x terms on the left and my constants on the right. Therefore, I'm going to subtract 8x from both sides, so I can move my x term to my left-hand side. 5x minus 8x leaves me with negative 3x, plus 20 is less than 12. Okay, I want my constants on my right, so I'm going to subtract 20 from both sides. Now I've got negative 3x is less than 12 minus 20 is negative 8. Okay, I'll stop there for a minute. Notice that for all the steps that we've done prior to this, everything has been addition or subtraction, and nothing is dealt with multiplication or division of negative numbers. Our next step, though, because we have to get x isolated, is when we divide both sides by a negative number, that inequality sign is going to have to reverse or flip. So that less than symbol now becomes a greater than symbol. So we've got, if we bring this up over here to the left, negative 3 divided by negative 3 cancels. 1 times x is just x. So we've got x now is greater than negative 8 divided by negative 3. Negative 8 divided by negative 3. Double negative should always be written as a positive. Positive is considered better than negative given a choice. And 8/3, you would want to reduce that fraction if possible. There is not a common factor. If you wanted to write it as a mixed number, you could. That's totally up to you. 3 does go into 8 2 times. 3 times 2 is 6. So there's 2 left over if you'd rather have a mixed number. The final thing they ask us to do is graph that solution. So draw your number line. You have to have a positive 8/3 on that number line somewhere. Our solution is values greater than that, so that would mean an arrow extending to the right. And then the symbol at the 8/3 would be an open dot. All right, let's do this problem here. Negative 0.6a is greater than negative 1.8. Okay, at this point, if you would like to clear the decimals, you can. Notice that for both of these values, the decimal number extends to the 10th position. So if we multiplied both sides by 10, that should clear out any of our decimal points and push the decimal point to the end of the number. Remember, for every multiple of 10 you use, it'll push the decimal place 1 to the right. So if you multiply both sides by 10, that's going to give you now negative 6a is greater than negative 18. Now at this point you want to isolate a, so we're going to divide both sides by a negative number, which as always means you're going to have to reverse the sign. Do the math. Negative 6 divided by negative 6 is 1. 1 times a is just a. Right-hand side, negative 18 divided by negative 6. 18 divided by 6 is 3. Negative divided by negative is a positive. Graph the solution. We want values of a that are less than 3. That would be to the left of 3, but it is less than, not less than or equal to, open dot symbol at 3. All right, let's do this problem here. First step, we want to use the distributive property to clear out any groups. Now, notice that in front of that 0.2, there is a negative sign, so you need to distribute a negative 0.2. Another way to think about that, just like with equations, is subtraction is the same as adding a negative. So you are distributing a negative 0.2. So therefore, you have 0.2x minus 0.5 is less than 0.5. Okay? Now minus 0.2 times plus 2x, 0.2 times 2, if you do that math either in your head or on the calculator, would give you 0.4, and it's a negative 0.4 or a minus 0.4x. Again, 2 times 0.2 is 0.4, minus times a positive is minus. Okay? You could also write that as plus a negative 0.4x. It's the same thing. And then our next step, if you take minus 0.2 and multiply it to a minus 13, negative times negative is a positive, and 0.2 times 13, if you do that on your calculator, is 2.6. All right, we got rid of our groups. Now we want to clear our decimals. So each and every one of those just goes 1 point to the right of the decimal point. So multiplying everything by 10, we'll move all the decimal points 1 to the right and clear our decimals. So we're going to do that next. We're going to multiply our 0.2x by 10 minus 10 times 0.5 is less than, our sign doesn't change because we haven't started moving things around. 10 times 0.5 minus 10 times 0.4x plus 10 times 2.6. Multiplication of 10 will move all those decimal points 1 to the right. So now we have 2x minus, move 1 to the right here, minus 5 is less than 5 if you move that decimal 1 to the right, minus, move it 1 to the right, 4x plus 1 to the right is 26. So we've got 2x minus 5 is less than 5 minus 4x plus 26. Now our problem is very similar to the ones we've been doing. You want to get your x's on one side, your constants on the other. Notice that on the right-hand side here, you've got some like terms on the same side of the inequality. You'll have to move less things if you combine those, so let's do that. We've got 2x minus 5 is less than 5 plus 26 is 31 minus 4x. Okay, let's say that, just to do something different, we want to put our x terms on the right now and our constants on the left. Remember I said it doesn't matter which side you decide to move your x's to or your constants. So I'm going to choose to put my x terms on my right-hand side by subtracting 2x and removing it from the left. So subtraction never changes the sign, so we have negative 5 is less than 31 minus 6x. Okay, and let's bring that up here. Okay. We want to move the 31, so we're going to subtract 31 from both sides. Subtraction does not change the sign. So we've got negative 5 and negative 31 is negative 36 is less than 6x. Negative 6x, excuse me. Okay, now, our next step is to isolate our x, so we're going to divide both sides by negative 6, because that will cancel out our negative 6 on the right-hand side and isolate our x. But when we divide by a negative number, you have to remember to reverse the sign. So do the math. We've got on the left-hand side, negative divided by negative is a positive. 36 divided by 6 is a positive 6. Right-hand side, we've got our x by itself, and that's our solution. Okay, now we want to graph that on a number line. So if we draw our number line, we have to have a 6 on there somewhere. Now you want to be careful. You want to think about what this phrase says, because the x is on the right-hand side, which is not what we're used to. So we've got 6 is greater than x. That means that 6 is the bigger number. And if that's confusing to you, what you can do is you can take that inequality and you can flip the whole thing over. Just make sure that the arrow always points to the same thing it's pointing to in your original solution. Okay? Here, notice that the inequality symbol is pointing towards the x. So if you flip that over and you want the x on the left-hand side, then the arrow still has to point to the x. In other words, if you flip the x to the left-hand side, then the arrow, inequality arrow also has to flip. If this makes more sense to you, x is less than 6, then you're interested in numbers smaller than 6, extends to the left. It's less than, not less than, or equal to, so that we need an open dot, and we've got x is less than 6, not equal to 6. Our final topic for this section is set builder notation. There is one last thing you need to know in order to do some of the homework. The homework in this section, occasionally but not always, will ask for a new type of notation called set builder notation. For example, x is less than or equal to 5 would be written in the following fashion for set builder notation, where you've got the variable written here that is in the original problem. That represents all of the x values that are in the solution set, and then that vertical line represents the words such that. So we've got x such that, and then whatever follows that vertical line represents the restrictions on the set. In this case, the x values have to be less than or equal to 5. Notice that the bracket notation are those curly Q brackets there. Okay, so that particular set builder notation problem is read as the set of all x such that x is less than or equal to 5. So let's do 3 examples here. We want to write the following inequalities with set builder notation, where starting here, remember you are going to need bracket notation. Okay? Since the variable a is in this inequality, a is greater than -1, that is the variable that you will also use in your set builder notation. So we've got the set of all a values such that, and then you will write the restrictions, which is simply the inequality here. A has to be greater than -1, and then that will be also enclosed in the right-hand side of those same brackets. So it's really very simple. It's just adding a little bit of notation. For y is greater than or equal to 12, we've got our bracket notation. Now we've got the variable y such that y is greater than or equal to 12, and that is set builder notation for that inequality. And finally, for our double inequality, set builder notation is set up the same. we now have the variable x again. So we've got values x such that x has to be greater than or equal to -2, or if you read it left to right, -2 is less than or equal to x. But at the same time, x has to be less than 8. And so that would be set builder notation for that particular example. So this brings us to the end of Module 7, Section 2.7 material, and this also is the last video for Module 7. You should now complete the homework for Section 2.7 found in my math lab. When you have successfully completed the above homework, review all the material for Module 7 and complete the Module 7 exam also found in my math lab. After successfully completing the Module 7 exam, you may proceed to the Module 8 videos.